Good afternoon, everyone, and thank you for attending our Battery Packs for Medical Devices Requirements and Certification webinar. My name is Anton Beck. I'm the Battery Product Manager here at Epic. Before we get started, I just want to let you know that we will be muted during the presentation. If you have any questions as we move along, please enter them into the question panel located in the webinar control panel, and we will get to them all at the end of the presentation. If we don't have time to go through all your questions, we will be sure to reply back to you by email. Also, we will be recording this webinar and we'll be posting both the recording and the slides on our webinar website and YouTube channel. Our presenter today is Randy Ibrahim, our battery product development consultant. Randy has been active within the battery and battery charger industry since 1996. Randy's 30+ years of experience in military, medical, industrial, and high-volume consumer industries has given him a unique advantage when qualifying battery designs for use in these industries. Excuse me. His work includes pioneering the development of custom safety circuits and battery chargers for unique application and chemistries. As a result, Randy has received numerous patents in this area of work and has written numerous articles for industry trade publications. So without further ado, I will pass it over to Randy.
All right, thank you, Anton, for that. Greatly appreciated. Yeah, today's topic that we're going to discuss is battery packs for medical devices and some of the requirements and certifications for these battery packs. Today's agenda, we're kind of focusing on the primary differences between medical batteries and using standard off-the-shelf batteries, essentially what the differences are. Also, the safety regulatory requirements for a medical battery. And then we're going to cover some of the design features required to meet these regulatory requirements. And then there's more than just regulatory here. We really need to go beyond just meeting regulatory. That's kind of like the entry-level bare minimum to a medical battery. We want to see what design features we can add to these batteries to help mitigate some patient risk, and also at the flip side of that, we also mitigate business risk, which is also as important. Also, we'll cover a little bit on some of the transportation requirements, but nowadays they kind of overlap with some of the safety regulatory requirements due to some mishaps at some of the airports that quite a few years ago. So let's start off here with the primary differences between the medical batteries and standard off-the-shelf batteries. First off, the off-the-shelf batteries, there's no change control, which when you buy an off-the-shelf battery and you test it with your product, everything might be fine, everything's great, but what can happen is that battery could change. They're not going to give you change notices. The manufacturer doesn't even know who you are. You're just they just know they sold so many. So all of a sudden you're running along, you're great, you're in production, and the battery changes. It looks the same, but it doesn't function the same. And what happens is you're totally down in the water, or worse, one of your patients becomes injured as a result of some unknown side effect of a unknown change in that battery. So it's very important to truly understand. There are some exceptions, of course. Let's say you have a little aux sensor that goes on your finger, and you have a coin cell or something off the shelf, some AA batteries in a small little class 1 type or class 2 type medical device. Yeah, off-the-shelf batteries work in those applications because usually those are just information gathering type medical devices. Decisions aren't really being made, they're home use, and they're more for information for the patient, but no medical diagnosis is being made off of those devices. So there are cases where it makes sense to use off-the-shelf batteries. What you're going to find here is medical batteries focus pretty heavily on safety, performance, and reliability. And what you'll see is there's more robust protections within the battery. And since most of these batteries are custom in nature, those protections don't change. So there won't be any surprises in your product as it progresses through the life of the cycle of your particular product. And also higher quality components are used. We use a lot of even automotive grade parts. And these parts are traceable. They're from quality suppliers. Very important in a medical type device, so you understand exactly what you're getting. And also, there's some unique cases where medical batteries are used in really odd environments. A good example here is like an MRI type machine where you have really high electromagnetic characteristics, and you can't have any ferrous type materials in the battery. So any off-the-shelf battery is no-go. Reason being, you don't know what from one lot to the next lot, what materials are being used in there, and if they're going to actually work in your end application. Autoclaving we see once in a while, very high temperature cleaning. Most off-the-shelf batteries would fail miserably under that environment, and even a lot of medical batteries struggle quite often. And we avoid it if possible. Try to remove the battery from the product and what have you. We avoid it if at all means necessary. And also another thing with is very important is looking at is it really your battery in your product? One thing you'll notice, medical batteries in general cost a little bit more, sometimes a lot more than an off-the-shelf battery. So there's a lot of incentive for counterfeiters to go out there and make a battery that looks the same as your battery, but really the internals don't function the same. Maybe really inexpensive cells are used, what have you. So you really want some maybe some very thorough handshaking with almost what the same type of encryption that they use for credit cards transactions. So it's very difficult to use a counterfeit battery. A lot of medical batteries will have this, and it's in the manufacturer's best interest to use something like that to avoid any mishaps in the field. Because if something like that happens in the field, it's your name on your product that hits the headline news, not the counterfeit battery. So it's very important that you understand and treat the battery as a system as a whole. And kind of touched on this a little earlier, the serialization and traceability components are pretty common in medical batteries, especially the higher class type products. Extremely important to keep track in case there's any counterfeit components on a circuit board, what have you. You really want to be able to isolate that. Now, touching on some of the regulatory requirements, some of the highlights here of what's really required. There's a whole lot here. I mean, and this is just the tip of the iceberg, but you know, FDA does require certain things. And the most common ones in the battery world here, IEC 62133, fairly new in the grand scheme of things. It's replacing, for the most part, the UL 2054. I believe the 2054 is more stringent in a lot of ways with single fault failures that are tested. They actually go in there and fault out parts where that's not required in 62133. So all EPIC products we always design towards the UL 2054 because it's more robust, more stringent. And if it passes 2054, it's a slam dunk for 62133. UL 1642, that's at the cell level. You know, it's required even as an entry level just to get into the 2054. The cells are required to pass the 1642. There they have a whole other set of tests that are done at the cell level. These other three right here, they're more for the primary batteries. We touched some of this, but EPIC's Asian engineering group is more versed in this area. It's more packs that they would be designing here stateside. We develop a lot of the rechargeables and the more complex batteries we have built-in battery chargers, a lot of extra IO, GPIOs in the batteries, where the battery itself is almost like a subsystem power system for a medical device or other industries. We hit in anything, you know, IT, you know, boy, high use volume consumer, anything with the battery in it, we pretty much touch. But stateside, we really put a lot of different things in batteries, and we turn them into a power system where you just plug and play, throw the battery in there. We actually have power supplies in, various power rails. There's a lot of things we can do with the battery, and it takes the workload off your engineers and your engineering team to be able to put some of that within the battery. Obviously, there's some trade-offs, but if you get to that point, give us a call. We can go over what those are. In addition, there are a lot of subsets in the medical world. There's a lot of other requirements. Here's, I just listed a few for dentistry, you know, then you got wheelchairs. So if you are in some of these subset medical products, there's going to be some additional requirements in addition to just your high level basic FDA safety callouts. And here, I think I kind of made the type a little more larger here, more prominent. UN 38.3 is kind of like the gatekeeper of all the regulatory requirements. You can't ship a battery, you can't test any passing, you have to pass UN 38.3. So if you're an expert, the next few slides are going to be extremely boring. So I'd suggest you get up, grab a cup of coffee, go out, stretch your legs a little, and then come back in 5 minutes. However, if you don't know much about UN 38.3, just hang on to the edge of your seat. We get some really, really good material here for you. The whole spec on UN 38.3 is geared around transportation. However, all the UL 2054s, IEC 62133s, you cannot even go into tests in the labs without having passed this first. But with that said, if you look at these 8 tests, they essentially emulate the characteristics of what a battery is going to experience in transportation. And this all came around. There's one year, there's a pallet of CR123 primary lithium cells, whole pallet full, on a tarmac in the airport, and it's getting ready to be loaded onto a airliner, and a forklift went right through the pallet, right through the middle of it. They weren't paying attention. The whole pallet caught fire. I mean, it was a huge fire, and you can't put out lithium primary cells that easily. It just sat there and burned. And everybody sat around and watched this, and they said something needs to be done. There's a lot of energy here that we weren't aware of. They're in the past, they're also aware of gasoline, kerosene, explosives, things like that are all class 9 hazardous material, and it was never treated with much seriousness until this pallet caught fire. So that was the birth of 38.3. And so going through these individual tests here, the T1 test, and keep in mind there's 16 samples that are submitted, and these are done on the first 8. The first 5 tests and they have to be done in sequence because every test it affects the previous test. So the first 5 here, T1 through T5, is done on the first 8 samples. And also samples are cycled. So that way they have a little aging on it. I believe they cycle it 25 times, something like that. And so we go through the altitude simulation first. And this is the simulate transport under low pressure conditions. This could happen, let's say they lose cabin pressure, or they're being shipped in a portion of the plane that doesn't have cabin pressure. So they want to make sure that in almost like a vacuum, not quite that severe, but under a more vacuum type situation, that that these cells and some of the electronics don't fail. And essentially, if you go through here, they're stored for many hours at room temperature, and then after that time, you'll notice the pass-fail criteria for many of these first 5 tests is no mass loss. In other words, they actually weigh the battery before the test, and they weigh it after the test, and they look for a percentage mass loss, and it cannot exceed the allowable limits. No leakage, of course. So you think you put something in a vacuum, it has if it has a bad seal around a cell, you're going to get some leakage, and that's really bad because all electrolytes, they're working on non-flammable electrolytes, but today majority of electrolytes are flammable. So if you get a leakage and you get oxygen nearby and some sort of ignition source, you would have a fire, definitely. No venting, same thing as leakage to a certain degree. And a disassembly or rupture, that's pretty severe. Obviously, that's not acceptable, and fire, of course. And also, they do measure the voltage before the test, and they measure it after. They want to make sure there's nothing obviously weird going on with the up and running here. So anyway, the thermal test, it simulates for loss of cabin pressure, which would obviously normally translate in a change in temperature. And so we look at that, and they test for it. And I won't go through all the test criteria, but they do cycle it many times, which kind of seems odd to me in some ways, because if you're going to lose it, you're going to lose it once, not 10 times. But regardless, that's what the test is. And same criteria as T1. I won't go through those, but and essentially no adverse effects to the test. And now we have T3 test, which is vibration. This is essentially, UPS trucks and airplanes, when they hit turbulence, they vibrate. This will test for that type of transportation environment. If you notice, the frequencies are very low. They definitely kind of simulate what would be expected in a truck going over a dirt road, perhaps. And here, same thing. They want to make sure that the pack can handle that type of vibration. What's really important with the vibration, also the shock, the next T4, is there's a lot of questions that come about, like, okay, I have a soft pack, I have one in plastic, but okay, we're doing all this. We don't have time to create plastic molds yet, plus the expense and the machine time. What we do a lot of times, if your battery is going to be in a plastic enclosure, we'll 3D print that enclosure, and that's all they're looking for. They're looking for something mechanically that simulates what will be used at the end, and they want your cells and electronics in that 3D printed enclosure. Or if we're lucky enough and have a plastic enclosure, we'll use that. And the reason for this, they bolt this thing down to a test table, and they want to make sure that nothing's going to rattle inside that enclosure. So they want to make sure you have really good insulating materials, RTV, what have you. They want to make sure your nickel doesn't vibrate back and forth, kind of the stress test where it breaks over time, like any wire. And so it's very, very important to be able to test really something that's mocked up to be very similar to what the final product will be. Let's say you have a soft pack, which is just shrink wrap. They'll bolt that to a table, but they also know that that's how it's going to be shipped in the future. So it doesn't matter what, but we definitely, whatever the final product formation is, whether it's enclosed in a hard enclosure, soft pack, whatever, we need to make sure we're testing this vibration and shock in that same type environment, same enclosure. Pretty important to do, and we can actually shave a lot of time off using 3D printed parts for these batteries. And also on T4 here, shock, similar to vibration, it's mainly simulates the person dropping the box, which we all get dented boxes at our houses. And so same criteria, just different thing. It's acceleration versus vibration. A different axis and different timing. So it's well defined what it is. Similar pass-fail criteria as all the other previous tests. In other words, don't let it catch fire, nothing can leak. Okay, going to the last of the series that are done in sequential in series of the test of 8 of batteries, half the 16 that's required. The short circuit test is essentially if let's say your batteries are packaged incorrectly and they're rattling, bumping into each other in the box, and they're shorting out because you have exposed contacts. That's what this essentially emulates. Majority of our batteries, we have very safe electronic safeties, electronic overcurrent trips. We here it's really 55 degrees, I believe, is the actual test requirement, and but our test house uses 57, and but with the plus -4, it keeps us right where we need to be. But the in this here with the external short circuit, they just want to make sure that if you have a fuse in there, what have you, that it will not overheat, what have you. So, and it's done with fairly gently with a 0.1 ohm resistor, which is pretty generous. The guy allows for contact resistance and wire resistance, what have you. That's why they do that. And especially the pass-fail criteria, the external temperature cannot exceed 170 degrees C. With us using electronic safeties on the majority of our medical batteries, we never exceed this 57. I mean, it just instantly opens and life is good, stays open for as long as we need. And they go look for another 6 additional hours and just make sure that indeed the safety's kicked in and they stayed off, and no adverse conditions, hours later. So pretty overly fairly simple test. But a little further in this presentation, we're going to go over where this 170 degrees C actually does come into play. If you have a low cost medical battery, we'll touch on that a little bit later. T6 is for cells only. When we assemble these batteries, the cells themselves come in with UN 38.3 tested. And if they're not, then we have to do T6. But at a pack level, it's not required. And and so then T7 is overcharged. This one is normally a pretty severe test for a lot of packs. What they is they look at the manufacturer's data sheet, multiply the maximum manufacturer's charge current, multiply it by 2, which is pretty severe, and they do the same with voltage. And then they go ahead and hit this pack with this high energy. And in a sense, if the pass-fail criteria is you do not want it to disassemble, no fire within 7 days. So they actually let these packs sit around. But one thing you'll notice on T7 is they don't have the open circuit voltage like a lot of these other tests require, where it has to be 90%, what have you. They expect permanent failure of the battery pack under these conditions. And sure enough, very few of them do survive it. Some of our electronic safeties have no problem. They reset and life is good. And the pack, you could actually reuse it after T7 with the more sophisticated medical safeties that we put on these batteries. But for the simple devices, yeah, you won't get a working battery after that test. And then T8 is also forced discharge. That's at the cell level. And that's done on cells that come into our facility prior to assembly. And here are other tests. As I said, a lot of our Asian manufacturing engineers use these a lot less than we do. These are oddball chemistries, primary cells, things that we don't really touch here stateside a whole lot. We do on occasion when necessary, especially under ITAR, what have you. But for the most part, I just want to put them in here more for being thorough, and won't go over them or bore you with them. But they're there. Look them up if you use something outside of a lithium-ion rechargeable battery. And these also apply to other industries as well. So we understand, I spent a lot of time on this 38.3, reason being, there's a lot involved here as far as needing that for all these other regulatory requirements. So in order to meet some of the severity of that test and the other regulatory tests, here are some of the design features that are normally placed in these batteries to be able to survive. Probably the foremost important safety in to pass these tests is secondary safety in the battery for charge mainly, and it's absolutely required for UL 6601, which calls out 2054, and also information technology industry, which is kind of odd to me. They also calls it out, and so in 2054 is pretty severe in what it requires. Essentially, with 2054, I put in little parentheses here, a single point failure, and we'll cover that here on the slide. First of all, what a secondary safety is, it's really what it sounds like. It's secondary to the primary. It is 100% independent. It has its own safety ICs, has its own charge paths. I mean, its own trigger points. Everything's 100% separate from the primary safety circuit. So the primary safety circuit could go up physically in smoke, and your battery's still safe. That's why it's really nice to have this secondary safety. The primary safety does more. It handles all the basic functions, over voltage, under voltage, which under voltage is really important for cycle life, and then overcurrent, and sometimes you'll see over and under temperature a little less common, really more sophisticated packs, that becomes more of a requirement. Also, the purpose of the secondary safety is to protect the cell for overcharge in the event the primary safeties fail. And this can actually happen if you look down here. If the FET actually shorts, you have back-to-back FETs. If the charge FET shorts, then the safety circuit, the FET that's in series is reversed, and the body diode would still be able to transfer charge current to the cell, and there'd be nothing stopping it. But what's really important is, let's say that your input voltage is too high. The charger, somebody else used the wrong charge, what have you, and so you're pumping all this potential voltage in the form of current through your pack, and potentially the cells could be exposed to an overcharge condition. We understand this is extremely unlikely. I think probably hit by a meteor is more likely, but still, it's possible it can happen. And this is a kind of a layout here of what I'm talking about. Here's your primary safety. It does a lot of different functions. These monitor every single cell on the side. Secondary safety, totally separate IC, does the same thing. But the difference is, if the primary safety wants to blow the fuse intentionally, sometimes you want to do that. Maybe the pack is hit end of life and you don't want the customer to ever use it again. So this little line here, the safe pin, we can blow that fuse and turns it into a brick. Your protection Mosfets are driven by your primary safety. If UL gets their little finger in there and they short out that charge FET, and this charge FET has that body diode, here's a path to overcharge. The secondary safety will sense that overcharge, come out, turn off, blow the resettable fuse. Very unlikely that you're going to have an overcharge condition, and it's very unlikely that your FETs are going to fail, but it really helps prevent the battery itself from, or the cells themselves, ever being exposed from a adverse condition that could cause harm. We can a lot of times we'll want to use a FET switch in place of a chemical switch. So instead of that, on this last slide here, going back here, you got this non-resettable fuse. A lot of times that's not practical to use. So in a lot of our designs, almost all of them, we use a FET switch in place of that fuse that acts like a fuse. And the reason for that is there are a number of cases where you cannot use a chemical fuse, but you still need the secondary safety functionality of what that fuse offers. And one application is, let's say you have a 2-wire system. You might have a couple small current ones for field gauge and communication, but let's say all your charge current goes through 2 wires and all your discharge current goes through 2 wires. So you got a lot of current going through here. Most chemical fuses cannot handle high current, and we're talking hundreds of amps. They just don't exist. That's where FETs really shine. Same thing with high voltage. These are electronically driven chemical fuses. When you're talking hundreds of volts, they have voltage limits. They can't be used. So FETs, again, they shine in this environment. Medical applications, again, a lot of these chemical fuses don't have all the necessary regulatory approvals, and they cannot be used in medical applications, where FETs, they shine in this area, and they have all the approvals that, majority, I should say, have them as required. Also, you'll find that chemical fuses are very limited in manufacturers that actually make them, where FETs, there's hundreds of sources out there that make these FETs, and they're very reliable. And these last 2 points right here, they kind of go hand in hand. FET switches are resettable, where chemical fuses never are. For instance, a good example is, let's say that you're using a heat shrink pack, and during manufacturing, we're running this pack through a shrink oven, so the shrink wrap can wrap around the cell and the protection circuit. Some primary safeties with that little safe pin I had a few slides ago will send out a little signal because it says, oh, I'm over temperature, and it sends out a little signal to blow that fuse. Well, the only way the recovery you have, since it's a one-time fuse, is to physically replace that. And so you have to disassemble the pack, you have to go through, you have to rework the board, clean it. If you have conformal coating, then that creates another whole level nightmare in your life. So we use the resettable FETs. So during the manufacturing process, with that little signal set the trip, oh, no big deal, we'll reset it. We have a little hardware fixture in the final test fixtures that will bridge a couple of test pads, boom, reset. It's really a really nice feature, and your production yields increase tremendously. Now, looking through all what I've talked about here, a mouthful here at best, let's say, you saw the schematic there. There's parts, there's components, there's circuit boards. Let's say you have a very cost-sensitive product. You just don't want any of those circuit boards. You don't want any of that. It's very small, it needs to fit in a very small cavity. And we've done a few products where that was exactly the case. It is possible to pass 2054 using the safeties that are built into the cell, as long as you have a high-quality tier 1 cell with these safeties in it. You definitely don't want to use a off-brand cell that you know that does not include all these various safeties in the cell. But the primary safety that would help you is a CID device. It's a current interrupt device, and it actually looks at the internal cell pressure, and it's a one-time event. So if the when you overcharge a cell, internal pressure, just like temperature escalates exponentially, so does internal pressure. And the CIDs will trip. It's like a mechanical switch that just flips, and it will disconnect the current flow. Hence, it will disconnect any current from a charger going into the cell and protect the cell. And but for it to trip, the cell has to get up there in temperature in order to build the pressure. So there is some risk in failing your test if you exceed that 170 degrees C. On top of that, we sometimes add an extra layer of safety. You got the CID in the front of the cell here. We sometimes will add a temperature cutoff device. It's a thermal fuse, and it's actually looking at the cell temperature. A lot of times you bond it to the surface of the cell with a thermal bonding compound or epoxy, a thermal epoxy, and it can actually pick up the cell temperature. There's some thermal lag, what have you. It depends on how severe the overcharge is, if it can trip in time. But sometimes it can be done. We have actually passed UL 2054 using this method, and it worked quite nicely, and we stayed well within the low temperatures of 170 C. And 170 C, just for a little background, that is the surface temperature. The internal temperature is much higher. And there's a phenomena within lithium-ion cells. If you exceed a certain internal temperature, you'll get into a thermal runaway. And that thermal runaway could be very devastating, because the cell will take off and start firing. You've seen videos online about that, and you can't put it out. That's why they picked that 170 degrees C limit. So we'll look at some of the other features. Now, we talked mostly about the cell itself, the battery, some of the safety features. A couple other things more a little bit, I should say, at a system level would be the 6601 requires low leakage currents if you're charging a battery near a patient. The reason is, when you're charging, that charger has to be plugged into like an outlet or a mains. And so this becomes very, very important. If the patient is connected to the product and the battery is connected, then it is absolutely mandatory that there's a very low leakage current in the microamps, and also a really high isolation voltage for nearby lightning strikes, what have you, not to jump that gap, the isolation gap. And so you have to use a medical charger and or a power supply that's medically approved with the proper regulatory stamps and approvals. Very, very important, and it's absolutely mandatory, and 6601 calls it out. If it's not connected to a patient, then one of our products, we actually have an IV fluid warmer, which is pretty cool, and it's also a blood infusion warmer, and it is designed not to be operated when it's plugged into the wall. So we put in inhibit circuits. So if you try plugging it in the wall, it will disconnect the output to the patient, and it will not power whatsoever the medical device attached to the battery. And also, we went one step further, where you cannot inject any charge current into the output, because a lot of engineers will overlook that. It's like, oh, okay, you took care of the input, but you get some high school project out there, and some kid wants to inject current through the putting current in through the outdoor, and so we actually inhibit that as well. So it becomes fully isolated. It becomes accepts no in or out power energy whatsoever, and that's how we design our products. We go a little bit beyond what's normally required, because regulatory agencies never look at the output; they only look at the input. And when it comes to this sort of application, then also another thing that can be done, and it's fairly easy to do, is use unique connectors. You want to make sure, especially charge connectors, you want to make sure that the right charger is used. I mean, how many times have we walked up, in a box of chargers at our home, and it's like, which one goes to that light, which one goes to my iPad, and we're lucky enough, sometimes they are unique connectors, but in a medical device, we don't want to take anything by chance. And so we want something that's very unique. And most of our customers have very unique connectors on their products. So the wrong charger can never be used with, on their product. Another thing that's really come into play recently, recently being the last 10 years, but you've been doing this for 31 years, I guess 10 years is recently, but going into wireless charging, they're upping the wattage. Now, I think they're in the 10, even 15, 20 watt range, and really nice, because there's inherent isolation, really nice. Inherent leakage, there is no leakage, because they're essentially an air transformer, as if you really think about it. Wireless charging is a great option. You can waterproof your products. You don't need to have connectors. Something really worth looking into if, depending on your environment you're using your medical battery in. But that's something we can easily put into a medical battery. And then I'd like to go a little bit further here, going beyond just meeting regulatory. You know, it's really important because regulatory is just the bare bones entry level, kind of the rite of passage, what have you. But you really want to go beyond that. You really want to make sure, because it's in your best interest for your patients, your end users, and also your business model to go beyond what's required. And when I say that, I'm mainly referring to smart batteries. They really need to be considered. And really what they are, for those who are less familiar with smart batteries, they're nothing fancy. They're just a self-monitoring circuit that's in the battery that picks up all the voltages, the currents, battery age, life, cycle life, temperatures, maximum temperature throughout the life, maximum charge current, maximum discharge currents throughout life, any abuse the battery's experienced, transportation it's experienced, a million things. I mean, a million, maybe 200, but you get the point here. A lot of data is available, and what's really nice, you can make very good, wise business decisions based on information that's contained in the battery. And this doesn't just pertain to medical batteries. We do this on all, industrial batteries, robotic batteries. We do it on drone helicopters, wheelchairs. The list goes on. We do these type batteries on everything. Anything that where it's really important that the battery works cohesively with the end product. And I touched on making sure the battery is authentic. That's your battery, not a counterfeit. We touched on that a little earlier. Also, another thing, you can put in serial numbers, all sorts of different special manufacturing codes in your battery. So let's say that you go through a lot of expense of developing a battery, but you have a lot of different products, and maybe this battery is good for some of them, but not all of them. You can actually, but it all fits the same, different products. So let's say that somebody plugs in a battery, it's your battery. It was, you check the authentication, it's good, but you realize, hey, this is a small amp hour battery, and this particular product needs a large amp hour battery. You can flag your customer through the display saying, oh, wrong battery, use this serial number or this lot number, whatever. So it's really nice to be able to make sure the wrong battery isn't inadvertently used in your product, even though it is your battery. Another thing is end of life data. We don't normally wait like our cell phones, where we get so frustrated that it does, it only holds a charge for 1 hour and you can talk for 10 minutes. Medical products really don't work too well when your heart's only going to be pumping for 10 minutes. So we like to build in, we like to understand what end of life is. And sometimes we want to preempt that and maybe artificially put in define what end of life is, even though the battery is still fully functional. But all the internal parameters are telling you that it is aging to a point where you cannot meet your end product specifications and what your customer expectations are. So you want a good end user experience, and usually in the medical medical field, that means keeping your patient alive. So a good experience is usually a good thing to experience here, especially from a manufacturing standpoint. And so essentially, I mean, some of the rudimentary type stuff would be like voltage capacity, things like that. And also we look at how much does the battery age. We know the initial design capacity. We can look as the battery ages what the most current capacity is, and we can watch it as it progresses through the life cycle of the battery. When it gets down to a certain level that's not acceptable, we can raise all sorts of flags, set errors, so your system can pick it up, your system can read those registers, a lot of things. Anything's possible with these type batteries. And then also at normal internal battery parameters, if they're exceeded or getting close, it's good for your system to understand what those are. I personally would not be displaying those on display and cause panic. It's something that you can do. You can maybe ease up on your loads. You can change your operating parameters to maybe compensate for that. Let's say the battery is being used at extremely high temperature environment where internal temperatures are getting a little too high. Maybe you have the opportunity to say, oh, we really don't need every bell and whistle. Let's just cut back all those little extras and let's just focus on delivering energy to keep a patient alive. And so you can shed some of your loads, let the battery work at really high temperatures and not degrade the patient experience. We can go on here. The maximum cycle life is reached past expiration. We can put an expiration date in there. Expired. Boom, on this date, we shut everything down. Battery is a brick. We don't get that severe. Normally, we look at that date. Your system can look at the date, and you can start warning the patient, like, hey, next month this battery's going to be dead. In 2 weeks this battery's going to be dead. Things like that. And also, let's say, unlike a very unlikely event, there's a recall. Let's say we get a counterfeit part. One of our suppliers, since everything's traceable, we can dig down and we got some part from some supplier, and we find out, wow, counterfeit. What's really nice is you can write a little code in your system. You can go out and pull the battery, understand the lot number, date codes, everything else within that battery, and you can really confine any potential recall to a very small, narrow lot of products and not have to recall every product you've ever produced. Very important added benefit right there. That alone can easily pay for the added cost of a smart battery. So moving along here, we have more of an epic philosophy, I would say, is a unified system design approach, for lack of a better term. We really like to work with the customer, and we really want to look at the actual medical product. The earlier we can get into the design cycle, the better. The reason being is the medical product, the power supply, the battery, they all need to be designed as a single system. In the early days when batteries were not used as much, the customers come to us and say, hey, okay, we got this great product, we designed it, and now we got this little cavity over here, one down here, one over here, we can put cells, can you just kind of stretch them out on harnesses? And I mean, it was a freaking nightmare. So, I still probably have nightmares, but anyway, what's really nice is looking at early on in the design where the battery is located within a product. You got to remember these batteries are chemical. They're fluid in nature, and they're kind of every single cell is a different living entity. And when you put these in a product, you might have some cells really close to this really hot microprocessor. Other cells are near the edge of the product where it's nice and cool, especially in the operating room where there is frigid temperatures. Now, what happens is you get these huge thermal gradients across your battery, and your battery pack will never, ever reach its expectation of cycle life because these cells close to your microprocessor are going to age extremely fast. The other ones won't. You're going to get huge imbalances. So it's really important to understand, where this battery goes and where the best location is. Sometimes batteries can be used as a balance. Oh, it looks like my audio just got restored. Little warnings. And let's say you have a really lightweight product, and sometimes it's nice to put the battery at the bottom and create a little bow so the thing doesn't tip over. Also, cell impedance, very important. This actually impacts mechanical design. If you look closely at a battery, let's say you got a motor or some heavy loads, you need to use a power cell, not an energy cell, which has normally lower capacity. But you say, I need this very long runtime. Well, they can't coexist easily. So then we have to start looking at early on in our product development. We say, hey, maybe we need something like a power drill where you can quickly exchange batteries, throw it on a charger, put the new one in, swap it out, boom, you're off and running. And then you get the best of both worlds. We need to know that early in your product to help save you from having to redesign and waste a lot of money during your design process. And then going through extreme temperatures. Now we do cell heaters, anything from putting resistors on a circuit board that heat the cells to full-blown blankets, a lot of military EMS, any outdoor applications. we do a lot of those. And looking at a little bit further, I don't want to use up everybody's time here, but you know, one thing I found I stumbled across, what I found is quite interesting is a lot of patients are actually injured by incorrect use of a medical device than actually medical device failing on them. You know, and here us engineers are out there like focused, okay, if this fails, we have this backup system or backup of a backup, you know, so this thing will never ever break. But in reality, we got to make sure we got to step back a little bit and make sure that these products are foolproof. A lot of the features we put in, that the actual end user understands them and they don't misuse them. Also, we have to do a really good job of making sure that capacity, whatever's read out to the battery is real. If you're in an ambulance 30 minutes from the hospital and the battery says 45 minutes, you better have 45 minutes there. So, and so we need to make sure everything's properly reported. And also unique mating connectors, color code them, do whatever it takes. You know, make sure it's really, really easy for the you know, the end user to understand how these things. They don't have to look at the end of the connector. Oh, okay, that geometry fits here. Color code them. It's very simple, and you can prevent a lot of mishaps. Also, as a manufacturer, a few things that you really want to look at is the you know, give model numbers, provide as much information. As I said, color code your connections so they're not incorrectly or they're stumbling, wasting time while someone's potentially having a difficult time medically, and you're pulling out the manual trying to figure out how this battery works or your system. So make it easy for them. Any maintenance that's required on batteries, chargers, and cables. Is there a maintenance schedule? Do you swap out certain cables after a certain number of use? Things like that. They seem obvious, but they're not obvious until you explain them to the end user. And also, a big one that we always run into is how do you maintain these batteries, especially if they're used or if they're stored in storage? What state of charge? Can you use a battery when it's fully empty and throw it in storage for a few years? Unlikely. You're gonna have a brick when it comes out of storage. So very important to understand and be able to convey that information to the end user. And also when to replace batteries with smart batteries, that's less of a guesswork. Your smart battery can tell the end user when that time has come, or you can put a simple expiration stamp on the pack itself. So we're almost done here. Just touch on a little bit of transportation highlights. This one's a pretty quick section here on how to transport these. If you look at this, these are the main players in the transportation space. Recently, the International Civil Aviation Organization, they came up with, which I thought was pretty intelligent, that the batteries cannot be shipped when they're over 30% state of charge. So in other words, you can't sit there fully charged battery and ship it. That's against the law. You have to bring it down to 30% charge. But a group that we work with, George, pretty good guy, Rechargeable Battery Association, they're pretty smart. They kind of realize, well, there's really no real method to determine what state of charge. You just can't measure voltage accurately for every single battery out there and be able to determine state of charge. So you have to really work with the pack assembler, the pack designers, determine what that is. How do we determine it? When we build these packs, we receive cells because they have the same standard that we have to meet. So we actually receive cells around 30% state of charge, so we're pretty safe there. And our fuel gauges, when you push the button, also show it. Pretty cool stuff. Anyway, the next slide here, no, obviously this is all based around 38.3, you know, that gatekeeper I mentioned earlier. And so going on through here, on the next slide here by IATA, right here, sure enough, here's your 38.3. Did it pass? No, go back, redesign. So there's an endless loop. So once you pass 38.3, now you can start shipping legally. And I put these red arrows because this is how I normally ship personally. Because we have pretty sophisticated products, I can work with it quite easily. And so you have different criteria here. If a battery's containing equipment, there's certain like packing instructions that you have to follow. If the battery's packed with equipment, there's packing instructions like 966. I have a tendency to use this quite a bit. A lot of our batteries have chargers in it, and they have you know, other power supplies, what have you. So a lot of times I call it a power system, and there's a battery our batteries in a power system, so our batteries actually contained in equipment, which is by definition very legal. And so I'll use this a lot of times. And there's FedEx is really nice. You hit these two options right here, 3481 on packing instructions 666 and 67, 967 are really nice. You can click the little button and it works out well. So, and this only works for very sophisticated ones, or if you have equipment, a lot of times I'll ask for a customer for their equipment and just to ship it easily. And so we'll go down that route sometimes. This chart is readily available on iata.com or org, I mean. And this is really recent, last August was updated. So wealth of info, I strongly recommend. Just when you get to their website, just type in batteries and a wealth of knowledge will come up, and it's very good to stay up to speed on what the requirements are. So in summary here, we covered a lot of material, and we did cover the primary differences. Hopefully everybody understands using a custom medical battery allows you to sleep at night. You know what you're getting year after year, no surprises. Of course, class 1 medical devices, AA batteries off the shelf, no problem. You know, certain devices are very good to use with off-the-shelf batteries, but they're very limited in nature. Obviously, the big takeaway for meeting regulatory is the secondary protection, leakage currents are the big ones. There's a lot of other things, you know, crush tests, plastics, enclosures, but those are details that for another day. And then going beyond, we're a firm believer in it. We want to mitigate all possible patient risk. That's where smart batteries really come in. They can preempt battery failures. Strongly suggest using them. They don't add a huge amount of cost, but they definitely add cost. But also they add a lot of benefit to your business and to your end user. And then we just touched a little bit on the batteries. As you know, I reiterated many times, it's got to pass UN 38.3. If it doesn't, you're not going anywhere. And then also pay close attention to the 100 watt-hour limit. If you notice in the slide, a couple of slides back right here, all this right here, less than 100 watts, 100 watt-hour, 100 watt-hour. It's very, if you want to take airplane, take a battery on an airplane, you really need to pay attention to that limit. And a lot of times your design decisions will impact what that is. And sometimes we'll put two independent batteries in the same enclosure, each one being 100 watt hours, and that seems to work quite well as well, as long as they're electronically independent. So if Anton's not asleep by now, I like to make sure give him an opportunity to go over some other Epic's great products that they offer their customers.
Thank you, Randy. While Randy reviews the questions that came in, I wanted to briefly mention some of our additional PCB-based products we offer here at Epic. Custom battery packs, flex and rigid flex PCBs, cable assemblies, RF products, high reliability user interfaces, flexible heaters, and our energy efficient fans and motors. Next slide, please.
All right. Yeah, I got a few of them. I'm not a speed reader, Anton.
Oh, okay, sorry.
It's supposed to slow motion here. Anyway, going through some of these, picked up a few here. This first one, hopefully I'm reading this question correctly. I believe what it's asking. If not, please, if you're the one who wrote this question, please email me and clarify for me. But what I believe that what the question is it seems like secondary protection circuit is unnecessary expense when there's a good chance cells will pass anyway. Why add it? And then also they're wondering if they can request not for it to be added. Absolutely, we're flexible, and as long as the manufacturer who's requesting this understands some of the risk. If you exceed the 170° before the current interrupt trips, then you fail the test. But if you're below it, it's great. But our philosophy too is we're not just out to pass tests. I mean, because that's a one-time event in the grand scheme of your entire product. we want to make sure it's safe also in the field. Even though it passes all these UL and fancy IEC tests, we also want to make sure it's routinely repeatable in the field in case there is a failure. But by all means, and we do it all the time, there's some very cost-sensitive products or volume constraint products. By all means, we can eliminate a lot of that and just rely on high-quality cells that we can supply. So that most definitely, and that's a great question. Let's see, another one. I have to pick the easy ones. Anyway, okay, let's see. How easy is it for the end product developer to access data in the battery? You didn't cover that, and we're kind of curious about how that's done and what type of interface is needed. Great question. In fact, I probably should add that next time. First of all, we use a lot of TI impedance tracking field gauges. We kind of enjoy them, that they're very accurate and less work on our side. And they interface primarily using I2C or an SM bus. And the SM bus is nothing more than a subset of I2C. And so fairly easy to use, but kind of keep in mind some of the field gauges, mainly the older ones, they have a tendency, they have the same address that's not I2C address that you can't really change. They're set. The newer ones you can set to a different address. But if that's the case, we've gotten around it. For instance, we have a artificial lung customer who uses 5 batteries in parallel, and they actually use a MUX to go out and point to each battery and communicate with it and then readdress it. So extremely easy to do, and it's definitely I2C based. So keep in mind, most of these are, since batteries operate slow, there's usually a 100 kilohertz limit on the bus, even though the bus can go up in megahertz. Batteries don't like going over 100 kilohertz. So keep that in mind. Sometimes you have to have a separate I2C bus separate from what you're currently using. Okay, and then another question here. Let's see. It almost goes in line with the first one, but why use a TCO when you have a CID in the cell? Yeah, this kind of goes in hand with the first question. The first thing is redundancy. We like redundancy in especially medical batteries. TCOs, they use temperature, where the CID uses pressure. They go hand in hand. They almost map identically, but it's nice. You can actually set the TCO to a little lower temperature, which would translate into a little lower pressure than what the CID would trip at, and therefore greater chance of being able to pass the test. If you want to rely strictly on CID, that works, and so that goes hand in hand with that first question. Let's see here. Oh boy. We got one here. It says, it's kind of interesting. Yeah. I thought I touched on this. Maybe I didn't. Are secondary protections only used for overcharge? Yes. Secondary, if you look at the primary safety, it does overcharge, undercharge, cycle. I mean, it does a lot of different things, overcurrent. The main thing that can cause a fire is overcharge. That's where you can't put any more energy in. They're unlike nickel metal hydride, where they just exert the energy as heat. Well, lithium-ion doesn't have that mechanism built in. So if you overcharge a lithium-ion, it will erupt and cause electrolyte to be exposed, hopefully to no flame and what have you. And so, yeah, it only looks for over voltage and never looks for under voltage or anything else. And so, great question. But yeah, that's they are strictly for overcharge detection, nothing else. And let's see here. I think we have. Let's see. Oh, I'm way over. I got time for one more, and then we'll answer the rest of the questions via email. But okay, this one here is towards the end of your presentation. You mentioned a 100 watt-hour limit when shipping by air. What exactly? What exactly does putting 2 batteries in an enclosure? How does it get around this? Okay, I did mention, they have to be independent, and that was actually to your point at the very end of the presentation. And I did mention that you can do that. And if you go back here, I'm going to bump back here a few slides because this is a good question. Right down here, if you look closely, let's see, where is it? Right here. Hopefully you can see my mouse wiggling here, but there's 100 watt hours equals 2 batteries. You can actually package 2 in, and it's totally legal. We actually have a letter stating it's legal to put 200 watt hour batteries in the same enclosure, as long as they're independent safeties and they're totally independent batteries. And what we do is when we plug them in to the customer's end product, it electrically either puts them in parallel or puts them in series, and you get twice the energy so you essentially get 200 watt hours. Keep in mind, we also charge these independently. So each one acts as a separate battery, and it keeps them all nice and balanced over the life of the pack. And so they truly are independent, but they act as one once they're plugged in the system. Anyway, as I said, this is all the time we have. I went over a little bit, but I think it was well worth it. Went over a lot of material. So I definitely want to thank everyone for joining us today. And again, email Epic with any additional questions, and we'll be sure to get to them and answer them, and definitely keep us in mind for any of your new products that you need to develop in any industry. I want to emphasize that, not just medical. We also are very heavy in military, ITAR, a lot of industrial. We do a lot of industrial robots. I mean, large batteries, small batteries, you name it, we do it. And a lot of very high tech, and also some simple batteries that our Asian engineers are very, very good at as well. And so we do the whole gamut here in all different chemistries, not just lithium-ion. So again, I want to thank you.
Thanks, Randy.